Alright, so this is problem number 2. S plus 3 over s plus 5 times s squared plus 4s plus 5. So we definitely got a third order on the bottom. The question is this real distinct roots, real repeated roots, or complex roots? It's going to be the last one. Looks like there are complex roots here. So there's a couple of ways we can approach this. If you're comfortable working with imaginary numbers, you can work this just like it's any other problem and actually expand out the complex roots into the denominators of the problems that you're trying to work. It gets a little hairy when you try to make that into, you try to bring that back into the Laplace transform table to pull out, like your sines and cosines and things like that. So I think what we're going to do is try to not deal with the complex numbers, but instead build our expansion into a form that matches some of the things that we kind of know that the equation is going to turn into on our Laplace transform table. So I'm going to write it out like this. A over s plus 5 plus b s, that's probably what you're thinking right now, plus c s squared plus 4s plus 5. Okay, so we've done this before in class using the same form. That's because we know if it has complex roots, we usually end up with a trigonometric function. And so bs plus c matches one of those on our Laplace transform table, as you'll see here in a minute. So, one of the things to consider here is the numerator of our second term is not a constant, but actually has an s on it. So it's a first order polynomial. Yeah, so that makes things a little tricky. But remember, last problem we learned the cover-up method. So we can find one of our terms with the cover-up method, and that would be the a term. So if we cover up our s plus 5, so with s plus 3 over s squared plus 4s plus 5 is equal to a, and we need to set our s equal to -5. So that's going to be -5 plus 3, that's -2. That's going to be 25 plus -20 plus 5. So 25 minus 20 plus 5 is 10. So it's going to be -2/10 or -1/5. And yeah, that's right. -1/5. All right. So again, we just did the cover-up method. We covered up the denominator associated with what we wanted to find here, and then set s equal to the root to solve for a. We can't do that with the bs plus c because that's not a number. That's actually a term. So we'll have to do the cross multiplication for that. So let's get started doing that. So what we want to do, again, is multiply everything by this denominator. So that will make us end up with s plus 3 is equal to a times s squared plus 4s plus 5 plus, I'm going to go ahead and distribute this out, but that's going to be S plus 5 BS plus S plus 5 C. Alright, so once we're at this point, we can start trying to find some of those relationships to try to figure things out. So let's gather like terms. So it looks like for S squared, so I'm going to take this S right here and distribute it out into here. So that's going to give us S squared plus 5S. So for S squared, we have a B term and an A term. So we have A plus B S squared. For our S term, looks like we have 4A plus 5B plus C. So that's all times S. And then it looks like we have just 5C and 5A plus 5A plus 5C. Cool. And so this is all set to S plus 3. So that means, so we can set up these relationships. So there's no S squared term on the left side of our equation. So that means A plus B is equal to 0. That means 4A plus 5B plus C is equal to 1. Right, because there's one S over here. And then that also means that 5A plus 5C is equal to 3. So we know already off the bat that A is negative 1/5. So that gives us enough information just from this equation, and from this equation we can calculate B directly. So if negative 1/5 plus B is equal to 0, that means B has got to be equal to 1/5. If 5 times negative 1/5 plus 5C is equal to 3, so let's see, 5 times negative 1/5 is negative 1. So negative 1 plus 4 is going to be equal to 3. And so if 5C is equal to 4, that means C is equal to 4/5. Yep, and that looks right. So let's go back up here. So we determine that B is equal to 1/5, and C is equal to 4/5. Alright. So now let's write that out and try to find the inverse Laplace transform of that. I'm going to get another piece of paper. So that means our f of s is equal to, so I'm going to write these out in decimal form because I think that'll make it a little bit easier. Negative 0.2 over s plus 5 plus 0.2 s plus 0.8 over s squared plus 4s plus 5. Alright, so we're halfway there. We know what we want to... We have it in the form that we need to use the Laplace transform table. So let's do that. So we've got to complete the square. We know that the form that we want to match. Let me pull up the Laplace transform table real quick so I can write that correctly. Let's see, table of Laplace transforms. So it looks like we have this form, which is e to the at sine b of t is equal to b over s minus a squared plus b squared. So that's a little tricky. And then for cosine, trying to find it for cosine. I think sine is all that we need. One second. Yeah, so what we can do with this form, so we can leave our negative 0.2 over s plus 5, that's fine. But this right here, we can pull out an s plus 2 squared plus 1. So this is equal to 0.2 s plus 0.8 over s plus 2 squared plus 1. Right, see that? So in this case, b let's see what identity that they're using. Generic decaying oscillatory from the Laplace transform table. Generic decaying oscillatory. Ah, okay. They're using the form b s plus c for s plus a squared plus wd squared. goes to e to the negative at b cosine omega dt plus c minus b over omega d times sine omega d g. So that's the identity that we're trying to push this portion into. So it looks like our B and C are actually the B and C that we calculated up here. Our A is 2, and our omega D is 1, which is convenient. We don't have to really worry about multiplying any of that out. So, keeping this identity in mind, which is in the table in the book, we can now say that f of t is equal to, so that one's easy, that's just negative 0.2 e to the negative 5t plus, so now what we can do is let's put our e, so our a here is our 2 here, so that's going to be e to the negative 2t. That's going to be times b, which our b is 1/5, which is 0.2. So we'll put 0.2 cosine t. So 0.2 cosine t, because our omega d is 1, plus, so now it's getting a little hairy. That's going to be c, which is 4/5, or 0.8. So 0.8 minus a, which is 2, times b, which is 1/5. So that is going to be, let me get that straight, 4/5 minus 2/5 over 1, so that's going to be 0.4. .4 times sine omega dt, which omega d is 1. So times sine of t. And I think that just about wraps it up. So this is our equation here. A little bit hairy, but not too bad. Once you get used to using this identity a few times, it's not that bad. And this is the identity that's commonly used for when we're doing partial fraction decomposition when there's complex roots. So this method is still a lot easier in my opinion than trying to actually pull out the complex numbers and use Euler's equation to get back to your trigonometric functions here. So yeah, not too bad. There might be something kind of like on this test, but maybe kind of like this on the test, but maybe a little bit easier. Yeah, so I'm going to go ahead and make a video for the next problem.